Madrid y esperemos que se quede. Bueno, ese es nuestro objetivo. Aunque no lo...
Nice.
Pia se ha licenciado en Buenos Aires, si recuerdo bien. Ha hecho muchos postdoc, Brookhaven, Regensburg.
Compostela. Compostela.
Y Santiago de Compostela. Y nada, es una experta en distribuciones partónicas y fiteos de distribuciones partónicas, es decir, sacar información del movimiento de los quarks dentro de los hadrones, ¿vale? Ver los experimentos e intentar sacar todo tipo de información. Y hoy nos ofrecerá un recorrido sobre este tipo de física que se llama appunto quarks y gluones, la vida interior del protón. Supongo que es muy interesante, así que muchas gracias.
So first of all, thanks for being here, and I'm sorry this will be in English because last time I had to give a talk on physics in Spanish, it was a nightmare for me. So I apologize for that if you're not used to. I will start telling you about the standard model of particle physics, and then I will take you in a short trip through the last century or so to tell you how we got here in particle physics. Then I will talk about the Parton distribution functions, which are my research topic mostly, and then very briefly what the future has in store for us. So standard model of particle physics. As you all know, there are 4 forces in nature. All of you know about the gravitational force. Anything that has mass interacts gravitationally. And the electromagnetic force for things that have electric charge. Then we have the weak force for things that have something similar to the electric charge, but it's called the weak charge. And the strong force for things that have a color charge. And the nuclear forces are just a residual of the strong force, actually. And these are organized like this because gravity is weaker than the weak interaction, very much weaker, 10 to the 32 times weaker, much, much weaker than the electromagnetic interaction, and even weaker than the strong interaction. The thing is that the strong electromagnetic and the weak interactions are very short range. So in the big scheme of the universe, gravity wins, but at very short distances, when we talk about protons, neutrons, then we really have the strong force and the electromagnetic force winning the game. Okay? So for particle physics, gravitational forces are completely irrelevant most of the time, not always. Okay? And these interactions, we understand them in terms of particles exchanging particles. So we identified 2 types of particles. First of all, the bosons. These ones are the photon, you all know. Gluons, Z bosons, and W bosons. They have integer spin. Spin, for those who are not aware, is a quantum property which behaves at the quantum level similarly as angular momentum, but it's not angular momentum. There's nothing spinning. We just call it spin. And particles with half integer spin, which I'll call fermions, and these are the electron, the muon, and the tau, which are just heavier than the electron. 3 neutrinos and quarks. And quarks come in 6 different, what we call flavors, probably because smell is a really bad word for this. These are called the up, down, strange, charm, bottom, and top. So anything that has electric charge exchange photons, and that's how they interact. Anything that has a weak charge exchange W and Z bosons, and or Z bosons. And anything that has a color charge will interact by exchanging gluons. So that's the standard model of particle physics. Let's go through time to learn how we got here. And I pick a point in time, which is the beginning of the 20th century, when we first understand how the atomic nucleus is made of. So before the end of the 19th century, this guy called J.J. Thomson, he found the electron, he measured properties of the electron, and he made a model for the nucleus, for the atom. So the atom has a lot of electrons going around, they're very small, and he said, okay, maybe all the positive charge that make it neutral is just like a soup of charges there. So if we do this kind of experiment, we have this source of alpha particles, which are some particles that some unstable material emit, and you hit a small, very, very thin foil of gold, for example, just to put something, you should not see a deflection because some of the particles will be deflected up, a bit low, but there will be a very small deflection. Small means 0.018 degrees, very, very small. That's the calculation. Of course, this is not true. Enter in Ernest Rutherford and his experiments. And actually, he didn't do these experiments. He just led the group. The experiments were done by his postdoc and student. So they did this experiment, exactly this experiment, and things look very different from what was expected. So Rutherford comes up with a new model for the atom, which consists on having a nucleus where all the mass, or most of the mass, and the charge, the positive charge, is all together in some very small, very, very small space. And this would explain why some particles are strongly deflected, why some particles just bounce back, and why some particles do not get deflected. Depending how close you are to the nucleus, you will be rejected, or you will be, if you're far away, you would just go through without changing. If you're very close to the nucleus, then you will be deflected significantly. Not a bad thing, okay? So we learned two very important things from this model, from this experiment, sorry. First of all, if you hit something, you do a collision with something that has an inner structure, you will learn something from the outcome of that collision, okay? That's really important. The other really important thing, especially for the students present here, is that whatever you do for your diploma or your master can be groundbreaking, because at the time, Marsden was just an undergraduate student. As you see, this is important. So we have now a nucleus, beginning of the 20th century. We know that the atom has a nucleus. What is the nucleus made of? And entering Patrick Blackett in the following years, he manages to do in the laboratory this reaction. Started with helium and nitrogen, and he gets oxygen and a proton. An important thing for this is that this is the first ever artificial transmutation. Granted, he never got gold, but he did something that people have been looking to do for centuries, which is merging together two elements to get something new. And then, all the time in this kind of processes, you get protons going out. So people start thinking maybe the proton is just the fundamental block of matter. This, of course, doesn't make any sense, because if you sum the number of, you know the number of electrons, you know how many protons you must have in the same atom for it to be neutral, and then you consider how much the mass of a proton is, the masses just don't add up, okay? And on top of that, if you only have positive charges in the nucleus, it would break apart because of electrostatic repulsion. So this cannot be. There has to be something else inside the nucleus, something that is neutral, electrically speaking, something that is quite heavy. It cannot be an electron. It has to be something heavy, and something that can interact with the proton in order to keep the nucleus together, and not having us just being a bit of particles going around. So the world will be very different if that wasn't the case. So people worked very hard to get this until 1932, beginning of 1932, James Chadwick sends a letter to the editor of the Nature magazine, in which basically in one column, he says, I think we found the neutron. And 2 months later, he actually confirms the neutron is there. So we're there. We understand how atoms are made of. We understand how nuclei are made of. So we're done. And of course not. We're never done in science. We just have to continue searching. Why? Because after participating in this experiment, for this experiment of the gold foil, Geiger built a special kind of detector, the Geiger counter, and people started using it, and they found natural radiation. People were crazy about radiation at the time. Everybody wanted to shine in the dark. So people would do things like, let's take a very romantic tour to the Tour Eiffel. You go to the upper level, you bring your Geiger counter, and you measure more activity on the top than on the bottom. So you double down on how romantic you are for dating. You go on a hot air balloon trip, and you find that you go even higher, and you have more radiation. And then, if you have the money, and you can afford it, you go for dinner at the top of the Tour Eiffel, and you see that even during night, you still see all this radiation coming in. So it's not coming from the sun, it's not coming from the Earth, it's coming from somewhere else. So people start putting in a lot of detectors that were developed at the time, trying to figure out what this radiation were. And they measured the traces of this part of this radiation, which are particles, going through the detectors with different types of detectors. And they actually look quite cool. So how we understand this, we call this cosmic rays. We have particles coming from outside our Earth, sometimes from outside our galaxy, yeah? Very, very energetic particles that hit the upper atmosphere, and they create a cascade of particles, okay? And if you put this, some detector that has a magnetic field, you can understand if these particles have electric charge or not. Then we have a very dark period. We don't talk about this. I'm sure you all went to see Oppenheimer, so you all know what happened there. But after the war, we knew all these particles. We knew the electron, that was from the end of the 19th century. We got the neutron in 1932. We knew the proton already. People have found the positron, and that's fantastic because by 1928, Dirac had come up with a theory how to describe particles that are quantum and relativistic altogether. It's better than Schrödinger's equation. But his equation, his theory, predicts the existence of antiparticles. And the fact that antiparticles were found really backs up the theory. So we're crazy, but not that crazy. People have, with these cosmic rays, people have also detected muons, which are basically like heavier electrons, and the anti-muons, so the antiparticle too. And then these particles that they called pions for some reason, okay? So everything that is missing are the neutrinos. The neutrinos were found in the 1950s. And the missing antiparticles, so the anti-neutron, the anti-proton, which we expect to find by this point because we know the theory is not so crazy. And then we are done. And I hope you learned by now that no, we are not done. Because people kept measuring these cosmic rays and they found a lot of other particles, and really a lot. They gave name to these things. Many, 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 many particles, okay? Many. So, and by 1952, things became even worse because the first modern accelerator was built and started working. It was called the Cosmotron, which is a really cool name, actually. And it started working at Brookhaven National Laboratory in close to New York, okay? This allowed people to have control on the initial conditions because for cosmic rays, you don't control what nature gives you. It allowed people to install and develop detector technology. You cannot put a massive detector in a hot air balloon, but you can put it on the ground in your laboratory. And it allows you not to rely solely on cosmic rays to understand these particles. However, I have to say, cosmic rays are very interesting things. They are low cost in the sense that you don't need to build an accelerator. Nature provides that. That's fantastic. And also the particles that are detected in cosmic rays experiments reach much higher energies than what we can do in a laboratory, simply because nature is far more powerful than we are, okay? Way more powerful. And truly, they are really cool experiments, especially this one called IceCube, which is right next to the South Pole. That's also cold, not so cool. So we reached the 1960s, and we're in a bit of a problem, okay? Because there are all these particles I show you that we don't really need, in the sense that I am made out of atoms, protons, neutrons, and electrons. I don't need pions. I don't need cascades. I don't need delta particles. I don't need any of these things. And all these particles have very strange behavior, some of them. So some particles barely interact with matter. These are the neutrinos. It took them forever to find the neutrinos. Particles that interact very fast, particles that can interact fast when they are created, but then they decay very slowly, comparatively slowly, of course. And people have no idea how to explain this, so they would come up with empirical rules, saying, for example, there's a quantum number called pinkness, and pinkness has to be conserved, therefore this process conserves pinkness, and it's possible, and this other process doesn't, and then it's not possible. There was no quantum number called pinkness, but there were some very strange ones. So we must find some sort of explanation for all this mess. And the first step, or the first thing you do whenever you want to find something, is call your mom. And of course, your mom will find it. That's usually how it works. Mine is too far away, so the second option is go to Mendeleev. Mendeleev was a Russian high school science teacher who came up with the periodic table of elements in 1969, the first version, and he put things in order. And once you put things in order, you start seeing the patterns behind it, and you start seeing the structure lying beneath it. So that's the idea. I always claim you have to do what the motto of Brazil says, which is order and progress. So let's put order. And in 1961, that's exactly what people did. People start organizing all these particles that have been measured in different patterns according to their properties, according to their masses, according to a quantum number called strangeness, which strangeness basically tells you how strange this particle seems to you, looks to you, because they behave very strangely. The higher or the smaller the strangeness, the worse the behavior is, the more strange. And the people built these 2 octets of particles and also this triangle, which is called the decuplet. And actually, this particle, the omega minus, was predicted by Gell-Mann. The properties were predicted, and then it was found. This is exactly what happened at the end of the 19th century with Mendeleev and his table of periodic elements. So you see order and progress. So Gell-Mann and Zweig proposed in the 64 that the fact that you can organize these particles like this is because there's some underlying symmetry, underlying inner structure, just as atoms would have a neutron and a proton, and they would combine differently to give the atomic nuclei. Well, they claim that, okay, or they proposed that actually there are 3 types of particles that they call quarks, up, down, and strange. Each one has a very particular value of electric charge. People had never seen fractional electric charges, fractions of the electron charge, of course. And of course, there's also the strangeness here. And they said, okay, all these particles that we call baryons, they have 3 quarks. And the particles that we call mesons have 1 quark and 1 anti-quark. And this explains everything you see. Awesome. However, this is a theoretical idea, and I insist, even if I do theoretical physics, physics, by definition, is a natural science. We need empirical confirmation. If the theory does not explain what we see, then the theory cannot be 100% right. So the question comes up is, where are the quarks? Okay, let's move to the following decade, 1970s. In SLAC, the Stanford Linear Accelerator Center, people were doing this kind of experiments. You take a fixed target, and a fixed target is not like a target for archery. Is, for example, a tank where you put hydrogen or a piece of iron or calcium or whatever you want to do, and you hit it with an electron beam. And what you obtain is the electron gets deflected, so you can measure this electron going out. And also at the same time, a lot of other particles were created. And the thing is that, just like in Rutherford experiment, when you measure the angular distribution of this electron going out, you can understand the inner structure of the target. And if your target was hydrogen, you were studying the inner structure of the proton. Instead of looking like one scattering center of one small thing inside, it looked like there were 3. That was compatible with that. And Richard Feynman called these objects partons. Now the question is, are these partons the quarks that were theorized by Gell-Mann? So now we are in the early 70s. We have a proposed model for the proton or any kind of composite particle that had been measured, well, assuming they're composite, and they require the existence of quarks with very specific electric charges, with 3 different flavors, so the up, the down, and the strange. They must have also this color charge idea, and it comes in 3 also. They were called red, green, and blue. And they have to be bound in particles so that you cannot see them alone, because no one has ever seen a quark alone. And we expect never see it. And the only thing that were measured was the indirect existence of these scattering centers, the partons inside the proton. So it's not very promising until 1974, in what in particle physics is called the November Revolution, when two laboratories simultaneously presented the discovery of a new particle. Because one of them called it J and the other one called it psi. Now it's called a J psi. It's always called like that. And the J psi is compatible with being a combination of another quark, heavier, that they call the charm, and its own anti-quark. Okay? However, if you have a 4th quark, you should have a lot of other particles that you have not seen yet that contain this 4th quark. Okay? So it should be combined with the up, with the down, and with the strange to give more particles. And indeed, that's what happens. So here we have this decuplet I showed you before, the triangle, and here we have all the other particles with the charm quark. So it seems like the theory is going well. Then, following year, the tau lepton was found. Again, the tau lepton is like a heavier electron, really heavy electron. by the end of the decade, the bottom quark was found, and the theory tells us that if you have one quark, they always have to come in pairs. So we were missing one, and they actually built a whole collider to find it, and that was in 1995, the top quark. So this is, again, the standard model of particle physics. We have the 6 quarks that we know so far, the 3 electron muon tau, the neutrinos associated to them, and then the bosons that are used to interact among each other. Then we have the Higgs boson discovered in 2012, but it's not a force of nature. It plays a different role, a complete different role. Okay, so that's how we got here so far. And then let's move to my favorite topic, which is parton distribution functions. Now, after all this time traveling we did, we know a bit about what the proton is made of. We know that in this quark model from Gell-Mann, it has 2 quarks up and 1 quark down, and the neutron would have 1 quark down and 2 quarks, 1 up and 2 downs, and they are together, held together by exchanging gluons. If not, they would be alone, living the life, but it's not. So what are partons really? Just everything you find inside of one of these particles, quarks and gluons most of the time. Okay, now let's go to a bit of mathematics, but not much because I was told I could not use equations, so no equations here. So mathematically, how do we describe all these interactions? Through a framework called quantum field theory. It's very well studied. Each type of force has a different theory. They have different names, but I will not go into that. And the terms in the theory that in this quantum field theory that describe the interactions, usually, not all of them, but most of the time have this shape. You would have the charge, so if this were the electromagnetic force, it would be the electric charge. Let's call it G for now, but it's not the gravitational constant. Then this would be sort of like a function. It's not a function, but let's say it's a function that describes the fermions, so the quarks or the electrons, depending what you're looking at. There's just a small difference between this one and the one here. And then with A, I will call the boson, so the photon or the gluon or the W or the Z, right? So what you have is an interaction between 2 fermions and 1 boson. And instead of going into equations, what we normally use to summarize this is a pictorial representation created by Feynman, which are called Feynman diagrams. So for example, I would have here 1 quark coming in, 1 anti-quark coming in, and 1 gluon going out. And this is very simple. It just summarizes all this. And each vertex I have is proportional to this quantity here, the charge. Okay? So in this case, it would be the strong charge. Okay? But if I put an electron and a photon here, then I would have the electromagnetic charge. So I take my Legos, and any process I want to see, I just build it from these Lego blocks. So for example, here we have an electron coming in, a muon coming in. They will exchange a photon, and then the electron will go out, and then muon will go out. So this is made out of 2 terms of this kind, multiplied, sort of. Okay, good. That's the theory. Now, let's move on to the important part for me. And the theory, this really fantastic theoretical framework of quantum field theory, only tell us how elementary particles interact with each other. It tells us nothing about how an elementary particle interacts with something that has an inner structure. It will tell us how an electron interacts, for example, with a quark, but it will never tell us how an electron interacts with a proton. Okay? So there's a problem there, because we know how to describe the elementary part, but we don't know how to interact the thing we actually do in a laboratory. However, this theory does give us something. That is the factorization theorems. Some processes can be proven that you can split them in parts. And again, this is not an equation. So let's say you want to see the interaction between a proton A and a proton B. This is, for example, what is done at the LHC. So what you will see is that a quark from the proton will interact with an anti-quark from the other proton, and will give you a photon. They will annihilate to give you a photon. So the probability of proton-proton interaction will go like this. Okay, I have the probability of interaction between this quark and this anti-quark. This I can compute, the theory tells me. And then I will have to multiply it by which is the probability of finding that particular quark I inside the proton A, and what is the probability of actually finding that particular antiquark in the second proton. And then because I don't know which one will happen, I will have to sum overall possibilities I have, okay? And this probability of finding the quark inside the proton is a parton distribution function. Roughly speaking, of course, I'm keeping it to the easiest form of understanding this. And I always claim physicists are really bad at naming things because if you study probability, a PDF is a probability density function, which is a well-defined mathematical object, and it's somehow related to this, but it's not the same. So whenever you work on parton distribution functions and you have to describe the probability density function of the parton distribution function, as you can imagine, an article becomes a nightmare. Okay, let's go into what these parton distribution functions do for us. Well, they contain every single information you want to know about the internal structure of a proton, a neutron, or any other particle, okay? So if you want to know what quark down in the proton had for breakfast yesterday, you ask the PDF. They have every single information. And there are many types of this PDF, and I will present some of them to you. And they're fundamental to make predictions. So if you have an experiment in which your initial state before the collision is a proton, at least one of them, you need to understand how the proton behaves, how the partons inside the proton behave, before you can actually do anything. And they're universal, meaning that if I have a proton here and I want to do my experiment here with a proton at CERN, for example, it's the same PDF that if I wanted to do exactly the same experiment in Alpha Centauri. Okay? It's exactly the same, should be the same. A proton is a proton. These PDFs depend on something that we call the scales, which are related to the energies of the processes. How they depend on the scale, it's given by the theory. So you see, the theory is fantastic. And here comes the bad part. You cannot compute a PDF. You have to obtain the information from data. And that's where we enter people working on PDFs. So let's start exploring a proton in the simplest way to try to figure out the PDFs in the proton. So the simplest way is saying, okay, I have an electron coming in, an electron going out. It will exchange a photon with the proton. They have both electric charge. And if this wavelength is very large, meaning the photon has very little energy, then the photon will look at the proton and say, oh, that's a proton. It's just a small ball. That's it. It has electric charge. That's all I know. But if I do this with a photon that has very short wavelength, and that means very high energy, it will be able to see inside the proton and interact directly with a parton, directly with a quark. Okay? So this interaction, this exchange of energy, is called Q, in this process is called Q squared. It's just a scale of this process, okay? It's related to how much energy and momentum are transferred, because these are relativistic particles, so we have to talk about energy and momentum together. And if Q squared is large enough, you can destroy your proton. You can break it apart and really study the inner things of it. So let's do that. Let's break a proton, okay? And the easiest way of breaking a proton is exactly what I showed you before. This process has a name. It's called the deep inelastic scattering, or DIS for the friends. And it's exactly that. You get an electron coming in, an electron going out. It exchanges a photon, not with the proton, but with one of the quarks inside the proton. And then you have a lot of quarks here going out and gluons that were inside. Okay. So here the quarks move in the same direction as the proton. So if the proton is going in the z direction, the quarks, you consider everything is going in the z direction. They're not moving in any other direction, just together with the proton. And they have a fraction x of the momentum of the proton. It's called x for reasons. And of course, here you have an exchange of energy and momentum given by this q squared. And all the theory can be written in terms of these two quantities, x and q squared, all the theoretical prediction. So all you have to do is take again the probability of interaction between the electron and the quark, multiply it by the PDF, the probability of finding that quarks are inside the proton, and then you sum overall possible quarks. And that's it. You have the prediction. So in order to compare with data and to determine these PDFs, what you do is, okay, I will write my PDF as a function, depending on which quark I have in, depends on x, and depending on some initial scale, because I told you they depend on the scales. But the theory tells me how to convert from some scale to another scale, okay? Fantastic. Once I have that, I put everything together to get a prediction, and then I will compare with data in what usually you construct a quantity that relates the prediction and your data. In modern data analysis with machine learning, it's usually called a cost function. This is a cost function. And then you find the parameters that best describe the PDFs in a way that minimizes this cost function. And that's it. We have the collinear PDFs. Of course, this has a lot of technical details that I will not go into because you will kill me at the end of this. So how do they look? Naively, in the naive Parton model by Gell-Mann, you would expect to have a quark up, and a quark down, and they will all roughly have the same quantity of the proton momentum because it's very democratic, okay? They all share the same things. The masses are very similar, not exactly the same, but similar. So this is how you would expect your PDF to look like, roughly, okay? For the up, it will be twice as much because you have two ups, but each one will have 1/3 of the momentum. Not exactly 1/3 because they have to be kept together by the gluons, and the gluons must have some momentum. However, the proton is actually far more complicated than this. The other thing was too simple. And nature apparently doesn't like simple things. Because you have this quark up, and the quark down, but they can also emit and absorb gluons. And the gluons can emit pairs of quark and antiquarks, like here. And actually, the gluons can also emit gluons. So what you actually see or find inside the proton is, okay, the first up, up, down, as we had before, we call them the balance distributions. Then you would have gluons, okay? And then you have the quarks that were radiated by the gluons. So all of this is still the proton, okay? The gluons that were radiated by the quarks, like this one, and the gluons that were radiated by other gluons. So it's a mess. It's not as simple as up, up, down. It's a real mess. And then you would expect to have a valence distribution and a C distribution. So these quarks radiated, I call the C quarks. So people take the data from DIS and other experiments, and this is therefore a more realistic picture of a proton. So you take data from many experiments. In particular, this is from DIS experiments, but there are many others. I don't know why this looks so ugly. There are thousands of points, so people can take thousands and describe perfectly well thousands of data points, and extract the PDFs. So these are two different groups that extract PDFs, and as you can see, we have the valence distributions, exact shape that you were expecting, and also the C distributions. And you see here that the gluon is divided by 10, so there are a lot of gluons inside the proton. Many, many, many gluons. Oops, I'm running out of time. We can also extract what are called collinear polarized PDFs, in which the experiment is done in a way that you control the spin of the particles, and that is done with special spin rotators, special magnets in the colliders. Not every collider can do this, because it costs a lot of money. But then we also have other things. We have this in the DIS process, right? Sorry, we're going out here. We have all these quarks going out, this one, and the ones, because we broke the protons, we have quarks and gluons going out. I should have put that there. So what happens with that? Because quarks and gluons have color charge, and we have said that we cannot measure things with color charge. They don't like being seen. Apparently, it's not fashionable having colors. Therefore, what happens is a process, very complicated process called hadronization, in which the quarks start emitting gluons, the gluons emit more gluons and more quarks, and they all recombine together to give us particles that have no color, like protons and neutrons and pions, particles that have an internal structure. So this is, for example, in electron-proton scattering, you will have a proton coming in, electron coming in, the electron gets deflected and is detected. And we know this is an electron because it's detected in the first layer of the detector, which is called electromagnetic calorimeter, in case you want the details. And then from here, you have this quark that was just a quark at the beginning. It will hadronize. It will end up being a lot of other particles, and it will be measured in the outer layer of the detector. Okay? And this thing, what people usually do, is to draw here a cone, okay, and say, this is a jet. All the particles that are inside this cone I will draw is a jet, okay, all together. I just don't care which particles are inside, I will just call it a jet. Of course, if you only collide electron-proton, you will get 1, 2 jets, 3 at most. It's very simple. But if you collide proton-protons, as it happens at the LHC, you will find many jets. So here you have already drawn on top of the traces of the particles all these cones that identify different jets. This is an 8-jet event at CMS. They have to reconstruct it with mathematical algorithms. Not so easy, of course. But apart from that, one could say, okay, from these particles that are flying out, I just want to see pions, for example, or protons. Let's say I want to measure the protons that are produced at the end. And if that's the case, I will need something else to describe what is the probability that this quark that came out will end up inside the proton I measure. And that is described by another type of PDF, which is called fragmentation function. So you not only have PDFs for the beginning, you also have PDFs for the end. And then we can move on to something which is being far more ambitious, and it's, I don't only want to know how are things in the collinear way, right? So I want to know how particles are moving inside the proton in the transverse plane, okay? Not only I would have like a proton coming in, an electron coming in, and just all the quarks inside the proton going in the same direction. Now they can be doing the conga. I don't care. They are having a party. They're moving in every possible direction. So what you study is, for example, in CDs, semi-inclusive DIS, you study the proton going out, again. The hadron going out could be a proton, okay? You measure the momentum it has, and you measure the momentum that is transverse to the reaction plane, so transverse to this gray plane. And then you relate that to how the partons are moving transversely inside the proton. So we introduce something that are called TMD PDFs, so transverse momentum dependent PDFs and transverse momentum dependent fragmentation functions. And there are a lot of them. This is just a fraction of them. And everything, this is considering that you don't care about the spin, but if you care about the spin of the particles and you study in detail the spin of the particles, this becomes very complicated. So this is from the latest extraction we did in IPARCOS. So we have people here who work on this, and my collaborators, of course. So this is a TMD for the protons, for d quarks in protons, up quarks, and anti-up quarks in the proton, which depend on x, and also on the transfer momentum. This is the Fourier transform of that variable, of that quantity, okay? And here is for the fragmentation function into kaons. So you can study every single possibility. If you want to be even more ambitious, you can try to figure out, okay, I know how they move in the longitudinal direction, I know how they move in the transverse direction, but where are they inside the proton? Where are the quarks and the gluons inside the proton? And this is studied by a more complicated object, which is called a generalized parton distribution, which will tell us exactly where things are in the transverse plane. Of course, this object is far more complicated. It doesn't depend on just two variables. It doesn't depend on just x and the transverse momentum kt. It also depends on other variables. And it's far more complicated to extract because this process, which is key to find it, actually has the same signals, the same final states as other processes. So you actually have to separate those first to be able to separate those from the data. And then you also have to take into account that these generalized parton distributions don't enter so simply into the equation. They enter inside some integrals. So it's really hard and really tricky to actually understand them. And therefore, the GPDs are probably the least well-known of these distributions. So very briefly, what about nuclei? Because when you do a collision with the nucleus, things are a bit on top of everything. They're more complicated. You're not interacting with just one proton. You might be interacting with partons in different particles. Okay, it could be in one proton, it could be in a neutron, it could be in this proton, it could be in this proton, on the one on the back. So you don't know at the in first place. So we know that the neutron is similar to the proton, It just has one less up and one more down. But the nucleus is not just summing protons and neutrons. Of course it's not, because if that were the case, the world will be very different from what it is. And it is what it is. Therefore, it cannot be the same. And the cleanest example of this I found is the following. This is from an article from 1981, where people did DIS, deep inelastic scattering, using nuclei, and they divided by what you would expect if there were no nuclear effects in the nucleus, okay? Just the fact that you have more neutrons and protons in general. So these are some theoretical models from low energy physics, from nuclear physics. And this is the expectation. And this is what was found. So clearly, I think we all agree, after 1981, for sure, a nucleus is not the same as having protons and neutrons just flying around, sort of together, but not together. And they even write in the article, the result is in complete disagreement with the calculations in figure 1. If you doubt it, this is figure 1. Okay, it's completely different. So what happens? We can try to describe this with nuclear PDF, which is what I did my thesis on, my PhD thesis. And they are quite different from proton PDFs, and they're much harder to obtain because we have far less data, and we depend on the data we have. And these kind of differences that you see in DIS with nuclei, you also see in other observables. So for example, this is the semi-inclusive DIS, the ratio between semi-inclusive DIS with nuclei divided by semi-inclusive DIS with deuterium, or protons, if you want. And as you can see by the colors, the heavier the nucleus, so the xenon is the heaviest state measured, the more of an effect you have. So 1 would be having no nuclear effect, and clearly you see there's a nuclear effect. And this is very poorly understood because it cannot be described with nuclear PDFs. It has to be described with nuclear PDFs and nuclear fragmentation functions. So it really overcomplicates our lives. And here on the right, what you see is the ratio between jets measured at Atlas experiment in lead-lead collisions, so that's very heavy nuclei, divided by proton-proton. As you can see, the effect reaches 50%. This is not a mistake. It's so far away from 1 that there's no way this is a mistake from the people doing the measurement. Okay? There's a very strong nuclear effect. And the fact is that these kind of things are not understood at all. There are 1,000 models trying to describe this, but all of them fail at some point. Good. So for the last part, let's talk about the future, but very briefly. So how do we improve our knowledge of the inner structure? We need more information, because we depend on data. You can do your calculations in the theoretical framework as complicated as you want, but if you don't have the PDF, you cannot do a prediction. So we need the data to extract the PDFs so we can actually compare with real measurements. And to do that, we need the data to have more data than what we have, but also more precise data and covering more of the kinematic space, because if I only look at the corner of the possibilities I have, I will not be able to extrapolate. Or I will be able to extrapolate, but it will be complete nonsense, okay? So we need more. And there are a lot of proposals. So all of these are proposed experiments. Nothing is yet approved except for the one in red. So people are proposing to build electron-positron colliders, or proton-proton colliders, more complicated, or electron-proton colliders. And EIC, which is in the next slide, is the only one that is on its way. Which one of the others will happen? Well, some of them are proposing China, so China has the money to build them if they want, I guess. But some of them are proposals in which Europe is involved, and this year is the year that the European strategy for particle physics will be decided, so they will decide what will happen in the next 20 years or so. Okay, so let's talk about the EIC, because we are also involved at the EIC. So what's the EIC, or electron-ion collider? There's currently a collider in the United States, in Long Island, called the Relativistic Heavy Ion Collider, or RHIC for France, which is currently the only polarized proton collider. It collides proton-proton or proton nuclei. And they have all the infrastructure, everything is there. They can run different species. They can run from proton to uranium. And currently, they have only 2 detectors working. Originally, they had 6. And it will stop July this year. After July this year, they will dismantle this collider to put the EIC in place. So the idea is very simple. They will remove this blue line you see here, which is one of the tunnels where one of the beams is going. So you have one beam going on the blue, one beam on the yellow, and when they reach the detector region, they make them collide. So that will be removed completely. To build the EIC, only one of the rings will remain. Then they will put a ring for an electron, so this will be an electron-proton collider again, which will have high luminosity, which means they will collide many, many particles, much more than any other experiment before. Okay? And they will also run in polarized mode, which will be the first time ever. No one has ever collided two beams polarized, an electron-proton, at the same time. Okay? And they have, half of it is done already. They just have to refurbish a bit and move things around. And they're working now in installing everything else. They have all the technology, and everything is set to do that. Also, one of the detectors is already on the way of being built. There might be a second detector, we don't know yet. But this one is quite advanced, and people are already building it. And with this, I reached the end of it. This is just the tip of the iceberg. Particle physics is a much broader and richer field. So in the theory department, we have a lot of people working on particle physics in different fronts. So you can drop by and ask if you're interested. And thank you very much for being here.
Thanks a lot, Pia. Very beautiful introduction to particle physics and the subject of quarks. And I think it has been appreciated also by the public. So now time is for questions. Every type of question. Don't be shy, especially youngest.
And you can ask in Spanish. I'm willing to answer in Spanish.
Podéis preguntar en español, no hay ningún problema. También contestará en español.
Sí, por supuesto. O está muy claro o no entendieron nada.
No, sí.
A comment. Okay. Try the other one.
No, está apagado.
Microphones. Okay, that's good. Yes. Well, have you tried the other one? Okay. Mm-hmm. Not the Geiger counter, no. Mm-hmm. I know, I have to keep it simple. Yes, because the Geiger counter cannot tell you how much ionization you get. Mm-hmm. Indeed. So. Esto está muy en contra nuestro.
¿Sí? Bueno, ahora sí.
Qué tímidos. ¿Nadie tiene preguntas?
5 minutos. ¿No va?
So first of all, thank you very much for the talk. So I'm curious about the amount of particles within a proton. So you mentioned we have these 3 quarks, then gluons, and then the quarks themselves will be emitting gluons maybe pair-producing other quarks, and so on and so forth. And you said that's a mess, but I'm wondering, I mean, is there a limit to the mess I guess those gluons which are going, which are being emitted are like virtual gluons or something like that? Or, I'm just trying to see if there is a divergence there.
Yes,
in
so
terms of
there is a limit
energy.
to that. In principle, you could have any kind of virtual particles, and for those who don't know, a virtual particle is a particle that behaves like a real particle, but doesn't have the correct mass. Okay, so in principle, you could find what is the probability of finding a top quark inside the proton. It will be a virtual top, of course. And you can also have electron pairs and muons or whatever, and photons and all of that. Now, about the divergence, that is what you get when you evolve, but at some point you will have to have something that stops that divergence, because it cannot raise infinitely, because in that case, the total probability of something will be higher than 1. Okay? And that is a problem, and that cannot be. So what we know is that some physical mechanism had to come into play when you go to real low x to stop that divergence. And that's called saturation. Now, how that saturation happens, we don't know, because we never reach a point at which we see that in the experiment. And that's something that maybe the EIC will be able to see in nuclei, because it's theorized that in nuclei it's easier to reach that point. But no experiment has so far reached a point in which you see that divergence going down or stopping or anything. So we don't know how that happens. It could be very well that the theory just says it has to keep growing, which is unphysical, and then that's where the theory stops working, because it has a range of applicability, of course, as usual, all theories do. But we don't know. We know saturation has to happen, something has to happen, because it's unphysical, but we don't know what. And that's a really controversial part of studies, especially in heavy ions.
Yeah, thank you.
There is one of your slides of the naive parton model. Mm-hmm. Can you put it on?
Remember the number?
In the middle.
Oh. In the middle.
Yeah. Where you say the sum of three masses of the quark. Yeah. Mm-hmm. So this was expectation when quarks were invented, but now you have come up with a picture where instead of the proton there are just not three quarks. There are these main quarks and couples of quarks, gluons, and so on. And if some students go in some textbook and say, oh, how much is the mass of a quark, of this up? They say it's half MeV. And how much is the mass of the proton?
Almost
say
1 GeV.
1 GeV. It's up to 30. Up to 30 we have time. Pero tenemos tiempo hasta las 2:30. Up to 2:30. Pero nosotros tenemos...
Vale. Let's cut it.
So we book up to 2:30, we stay up to 2:30. So the sum of these three quarks is not 1 GeV, which is the mass of the proton, is much less than 1 GeV. So we need all these particles. We can say more about this.
Yeah.
And we need the spin.
Well, neither the masses nor the spin of the proton come up from just the masses of the quarks or the spins of the quarks. It's very well known by now that the gluons contribute to the mass of the proton, despite the fact that the gluons don't have a mass. So it's the interplay of all these particles that basically construct both the mass and the spin of the proton. And that's something that is being, of course, under research, but it's very hard to tackle. And that's the most I can say, because they kick us out.
Probably if there are no more urgent questions, we leave our colleague to do their classes. Yeah, we stop at this. Thanks a lot, Pia. It was a pleasure.